All right, well, good afternoon, everyone. This is the electricity lecture. We're going to start with electricity, and that's going to lead us in a little bit later into something that is very closely related to electricity, which is magnetism. So we started talking last week about the atomic structure. And that was really important. I told you that was important for the topics that are coming up this week and then also next week. And what we learned about the atomic structure is that all atoms are made up of positive and negative charges. So we have the dense nucleus core, which is made up of protons and neutrons. And the protons are going to give a positive charge, neutrons are neutral, so they have zero charge. And then the electrons orbiting around the nucleus are negatively charged. So everything is made up of positive and negative charges. And that property of materials is going to allow us to look at electricity and to see how things interact when there is an imbalance of these charges. So the first thing, something that you probably have heard before, at least this saying, um, is that opposite charges attract each other. So positive and negative charges, there's going to be some force between those two charges that we'll define in just a second that pulls those charges together. And then like charges are going to repel each other. Two negative charges will push away from each other, also with a force, just acting in the opposite direction. And the same thing, two negative charges and two positive charges. Any two like charges are going to repel. Then, so we'll want to keep that basic property in mind throughout the lecture. So if we have an imbalance of electrons, then we end up with something called an electric field. And I want to go back and look at something that we talked about before, which was gravity. And we can kind of make a comparison in between the two here. So we have, when we talked about gravity, we talked about it as both a force, the attraction between two different masses, and then we also talked about it as an acceleration, the rate at which everything falls towards the surface of the Earth. So one way that we kind of left out that we also could define this as is as a gravitational field. Now, a field, we're going to learn about a couple different fields today. A field in general is going to be anything that affects the space around another object that will kind of alter the space around it so that if an object enters into that space, it can change its direction. So with a gravitational field, Earth has a uniform gravitational field that always goes down, points down towards the surface of the Earth. We know that if we throw a mass into that gravitational field, it's going to take a path somewhat like that, as well as I could draw in Keynote, a projectile motion path that goes down to the surface of the Earth. So what's happening there is even though it had a perpendicular entrance into that field, it still is pulled down. It takes that path of a projectile that we defined in week 1 and takes it down towards the surface of the Earth. So this was when a mass is entered into a gravitational field. And gravitational force and the strength of the gravitational field depends on two things. The masses of the two objects. The greater the masses, then the greater the strength of gravitational field and the greater the force between them. And then also the distance between the two objects. The closer two objects are together, then the greater the gravitational force as well. So this is an equation that's kind of a sneak peek into week 4. We're going to talk about something called Newton's universal law of gravitation, but it all goes back to week 1. So we can look at the same thing with electric fields, and it kind of acts in the same way. So anytime we have an imbalance of electrons, there's going to be an electric field in between those two different areas, different regions that have those different charges. And again, a field is going to be something that affects the space in between the positive and the negative charges. So what that means is that if something that's affected by electricity, i.e. something that has a charge, is thrown into that field, then that's going to change the motion or change the path of that object. So instead of having a mass this time we're going to have a positive charge or a negative charge, it doesn't matter which. Both types of charges are affected by electric fields. So if I take a positive charge and enter it in the same way that I did the mass into the gravitational field, then that object, that positive charge, is going to take a path much like a projectile towards the thing that it's attracted to. So that positive charge is going to be attracted to the negative charge, and it's going to follow the electric field lines. The difference between an electric field and a gravitational field is that the gravitational field is always going to act downward towards the more massive object. So like downward towards the gravitational field of the Earth is going to always act towards the surface. You know, things always fall to the surface when acted upon by gravity. With an electric field, depending on the charge, it can go to the right, it can go towards the negative, or if you throw a negative charge into that field, then it can go to the left. But the electric force is going to depend on, very similarly, the charge of the two objects and the distance between the two objects. The greater the amount of charge, then the greater the electric force. The smaller the distance between the two objects, the greater the electric force as well. So there's a very similar relationship between the two. And I'm going to show you the equation for electric force, and you're going to see when we talk about Newton's universal law of gravitation in week 4 just how similar this equation is to that. Just a couple of different variables. So the electric force equation is something called Coulomb's law, and it's a little bit, this is definitely the most difficult. It has the most components, has a square in it, the most intricate and complicated equation that we go over this month. But it's really not too bad if we just kind of break it down. So the electric force is equal to Coulomb's constant. This is a physical constant. It's going to be equal to 9 times 10 to the 9 newtons. Meter squared per coulomb squared. And every time if you have to do a calculation with for electric force, you're always going to be multiplying by that constant 9 times 10 to the 9th. And then on top of that, we have, on top of the fraction, we have the point charge 1, point charge 2. These are the two charges that the electric force is being calculated between. And then we also have the distance between those two charges. So you can see in the diagram there, charge 1, charge 2, and the distance between them is what this all depends on. And let's do just an example of that calculation. You guys, of course, know my process by now. You would write down what you're given. I think I just said this before the lecture, before I turned on the recording, but unfortunately my iPad is not connecting to the screen, so I can't write on the screen right now. So hopefully you guys can use your visual aids and I can use good verbal cues to lead you in the right direction here. But if I was going to write on the screen, which I normally would at this point, I would say, what am I given in this problem? And here it's just a picture, so it makes it even easier. I don't have to go through words or anything, but it says that I have two charges that are 2 meters away from each other. One charge is negative 0.26 coulombs, and the other charge is positive 0.45 coulombs. So my Q1 can be either of those, whichever one's your favorite. Q1 negative 0.26, Q2 is equal to 0.45, and then the distance is equal to 2. And then the only component that's left that I don't have in Coulomb's law here is that K, but of course I do have that, just not given in the problem. It's a physical constant. It's always 9 times 10 to the 9. So then my next step would be to figure out an equation that I need to solve for electric force. And of course, that's going to be Coulomb's law. Right away, I can plug in K, physical constant, will always be 9 times 10 to the ninth. That should be an exponent, not 9 times 109. That's not correct. And then I simply plug in my values. So with this setup, I like to take it step by step. I, of course, jump right to the answer in the next one, but I will describe the steps I would take normally to solve for this. So right away, I leave the 9 times 10 to the 9 where it is. My first step is to simplify that fraction, and then I'll multiply by 9 times 10 to the ninth later. So the first thing I want to do, make my fraction just look like a fraction and then like a number. So negative 0.26 times positive 0.45, whatever that works out to be. And then I would write that on top of the fraction. And then divided by the bottom of the fraction, to simplify that, I have to do 2 squared. 2 squared is equal to 4. And then I would take the fraction, simplify that even further, dividing by the top number by the bottom number. And then I would multiply by 9 times 10 to the ninth. And what I'd end up with is negative 2.63 times 10 to the 8th newtons. So what does this negative number mean? Does it mean that this is a really, really small force because it's less than 0? No. In this case, and in a lot of cases, you've probably already seen in this class, positives and negatives are used to indicate direction. And in this case, it's telling us, is this an attractive force or a repulsive force? So remember, gravity is always going to be an attractive force because it always pulls objects together. Gravity never pushes objects apart. But electric force, because we have different charges and different ways that they interact with each other, we have to indicate whether this force is going to pull the objects together or push them apart. So a negative value indicates that the electric force is attractive. And that would tell us, I mean, you might know that right away just from the example, because we said that opposite charges attract each other. So we had a positive 0.45 charge and a negative 0.26 charge. Because they're opposites, we know they're going to attract each other. And in fact, that's how it always works out mathematically anyway, because if you multiply a negative times a positive, then you'll always end up with a negative. So a negative value indicates that the electric force is attractive, and a positive value means that the force is repulsive. So that means that pushes them apart. So that would mean you had 2 negatives or 2 positives. All right, any questions on that? All right, so we define electricity in your course notes. We don't really split it up into 2 different types of electricity, but I just want to talk about the 2 main types here. The first one is going to be a static electricity. Static electricity is the buildup of charge on the surface of an object. So this charge, it's exactly as it sounds. Static means not moving, and that's exactly what this means, that the charges are not moving. They're just sitting still, and they're built up on a surface. So they're stored as a type of potential energy, but it doesn't actually flow anywhere. This is what happens. You guys are probably pretty familiar with static electricity. We experience it in our everyday lives, especially if you maybe scuff your feet across the carpet. What you're doing is you're building up charges on the surface of your body. And then you know that if you scuff your feet across the carpet and then go and touch a metal doorknob, you know that usually doesn't feel too great, because then the electricity will flow. But until it does that, then it builds up on the surface of your body, and that's static electricity that does not flow. This is also why if you build up enough charge, your hair stands up on end, and you end up looking like this little man in the picture here. And what happens is all of your hairs are going to be charged the same, um, maybe they're all positively charged, and then all your individual hairs being positively charged on their surface is going to cause a repulsive force between them. So when they stand up like that, they're trying to get as far away from each other as possible, and that's about as far as they can get before running into another one that's also positively charged. So that's separating them so that they're about as far away from each other as they can get. Um, and then on the other picture that we have here, if you've ever taken a physical science class, like this is a physical science class, but a physical science class in a classroom with a lab, you've probably played with the Van de Graaff generator before. And these are they're metal spheres that built up charge on the surface. So inside that little box on the bottom of the one on the left, there's going to be a little assembly belt that is rotating and kind of causing that friction the same way that it does when you rub your feet on the carpet, that builds up charges on the surface of the metal sphere. And if you put your hand on it, then it will charge your hair and you'll end up looking like the kid on the right, on the other picture. But if you put another metal sphere nearby, then that will give those charges somewhere to flow. And when that happens, then you get a streak of current electricity that passes from one charged surface to a differently charged surface. So this is exactly what happens, and you might look at that picture and say, wow, that kind of looks like a lightning bolt. And that would be a very astute observation, because that is exactly how lightning bolts, well, pretty much exactly how lightning bolts occur. So we study lightning, especially here in Florida. If you're a Floridian, we have a lot of electricity here, and we have one of the biggest lightning study labs down at my alma mater, which is at Florida Tech. But they're doing a lot of research on it because it's not as well understood as we might like to think. But here's what we do know, the very basics of what we do know. It's caused by something called charge separation within a cloud. There's some process that occurs that usually it's got to do with when there's a lot of humidity in the air and there's water vapor that's rising. That water vapor, those molecules interact with the molecules inside of the cloud, or the particles inside of the cloud, and then something happens, process isn't well understood, where the electrons are knocked off of the atoms inside of the cloud, and negative charges build up on the bottom of the cloud. So this is supposed to be a GIF file that's not actually working right now. But if you, at the top of the cloud there, the negative charges would go down to the bottom of the cloud. And when those negative charges build up and they're strong enough, if they keep building at the bottom of the cloud, what that does is actually pushes the negative charges on the ground away down underneath the surface. So, and brings the positive charges up to the surface, because negative charges repel each other, and negative and positive charges attract each other. So now what we have is a separation of charges. We have charges in different charges, a buildup of charges on two different surfaces. And we just learned a couple of slides ago that causes an electric field between them. So we have now the air in between those two charged objects is going to be a strong electric field. And eventually, when that electric field, that static electricity that builds up on those surfaces, gets too strong, then that's when there's that discharge of lightning in between through that electric field. All right, so electricity that sits still is called static electricity, and the opposite of that is going to be current electricity. And you might guess the opposite of something that's sitting still is something that's moving. So the current electricity is defined as the flow of electrons through different materials. So this is when those charged particles are actually going to be moving. Current is measured in amperes or amps, and the unit for that is A. The symbol for that inside of an equation is going to be I, so it gets a little bit confusing with the two vowels there. But 1 ampere is the rate of flow of 1 coulomb of charge per second. So this is a rate quantity. It's how many electrons flow past a given point every single second. The more electrons that flow, the greater the current. The less electrons that flow, the less the current. There you go. There's a visual in case you didn't know what I meant by electric charges moving. All right, we have two different types of current. We have DC, which is direct current, and this means that the charges will only flow in one direction. So here, the terminals of maybe of a circuit or a battery or anything, they have a set positive or negative charge. And so those electrons will only flow in one direction. Alternating current, which is largely more popular in household appliances and everything at this point, are going to be alternating in different directions. So you can change your terminal signs. So they're constantly changing from positive to negative so that the charges can alternate in direction. Like I said, most things in your home are wired in AC at this point. You can get electricity from the power company that sends electricity to you. You can also send electricity back to the power company if maybe you have some sort of green energy or like solar panels or a windmill or something like that where you're actually generating energy at your house. If you ever used less energy than you produced, then you would actually be sending electricity back to the power company, and they would have to send you a check as opposed to the other way around, which always sounded like a really nice thing to do. But so DC is direct current. Electricity flows in one direction. AC is alternating current. They flow back and forth. And as you might imagine, electricity does not flow, electrons do not flow the same through all materials. It flows really easily with low resistance through some materials, mostly metals. And then it also doesn't flow well at all through other materials, things like maybe like rubber. So we have different names for those. Electroconductors are going to be materials that have loose outer electrons and at least easily allow the flow of charged particles. So loose outer electrons means that they can be exchanged easily. They're very active types of materials. Conductors are going to allow the flow of electricity very easily across its surface. So some really good conductors, most circuits are going to be made out of copper. Silver and gold are going to be really good conductors as well. They're actually going to be better because they don't better than copper because they offer less resistance. So it's a more efficient means of getting electricity across the surface. The only reason that we don't build all our circuitry with silver and gold is because we don't want to pay tremendous amounts for them. So it's really just a cost thing. They are better conductors. I've been told by some of my students when I talked about this in class before that a lot of like high-end recording equipment and stuff like that use silver and gold circuitry just to be more efficient. But most everyday things are going to be copper, which is still a very good conductor. And then we move down, it's kind of a continuum here. It's not just straight, one's a conductor, one's not a conductor. You can have a better conductor than another. You go down to the middle here, you have something called semiconductors, and examples of those are going to be like germanium and silicone. Semiconductors are going to be objects that it's a very useful material because they can actually be either under different conditions. Silicone and germanium can be conductors under certain conditions, and they can be insulators under certain conditions. And usually those conditions that can be controlled are going to be temperature related. So as you increase the temperature of an object, it increases the resistance, and that would make them less conductive, and then the other way around. So they can be one or the other depending on, it's mostly temperature dependence. And then on the other end of the spectrum here, we have things that really don't conduct electricity well at all. Most of the time, if a charge is applied to that surface, it's just going to sit there as a static charge. It's not going to flow. So it's going to resist the flow of electricity. And these are going to be things like wool, glass, and rubber. So the atomic reason for them being insulators is that they have tightly bound electrons that will resist the flow of charged particles. All right, so I've used the word resist and resistance a couple of different times, and we kind of understand what resistance means just because the word resist means to push back against something. And in this case, we're talking about electricity. But resistance itself is a quantity of circuit components that's very important. As electrons flow through different materials, how much resistance occurs is something that we definitely need to calculate when looking at types of electric circuits. So resistance describes how much a circuit component resists the passage of electric current. The units for that are going to be ohms, and you have your symbol there, the ohm symbol. You can write it out either way if you have to do anything with that. Your circuit simulation for this week is going to be building circuits, calculating current, resistance, and voltage, which we'll define in just a second. And you can keep an eye out for either of those things, the word written out ohms or the symbol ohms. Just remember that's the same thing. So certain factors affect electrical resistance depending on a couple different things. The first thing we already just mentioned, it's bullet point number 3 here, but that's the material of the wire. Conductors like metals are going to have lower resistance because of that thing at the atomic structure, that they have loose electrons that can flow easily. So conductors have low resistance, insulators have high resistance to electric flow. And then the thickness of a wire. Thin wires are going to resist electrical current more than thicker wires. And even though electrons travel on the surface of objects, I always find it easy to think kind of like in the picture there when I try to remember this stuff. Picture maybe like a garden hose or something that's hollow when you have physical objects that are trying to pass through it. The real reason is that there's going to be more surface area for those electrons to travel on. So in a thicker wire, so it's going to be more electrons are going to be able to flow because there's more surface area for it to travel on. But in my head, I like to picture it passing through, and because there's a larger passageway, then more electrons can fit through it. So thin wires resist electrical current more than thicker wires. Long wires offer more electrical resistance because more energy needs to be supplied in order to push them over a greater distance. And then the temperature, I mentioned as well, higher temperatures offer more resistance, because if you remember our definition of temperature from week 2, temperature is the direct measurement of atomic motion. So if something's really hot, then that means that the atoms and the particles inside of that material are already moving really fast. And if you try to send more subatomic particles over that material, then that atomic motion is going to hinder that process. So higher temperatures offer more resistance, and cooling something down increases its conductivity. If you've ever heard of maybe the phrase superconductors, all those things are taking highly conductive materials and cooling them down to obnoxiously cool temperatures. And that's going to slow the atomic motion and allow for little resistance across the surface from the materials particles and allow those electrons to flow without much impedance. All right, so we're kind of building the components of our circuit right now. We've done two of our three main components. We have the current, which is the actual electrons flowing through a material. We have the resistance of that current, which is how much it tries to slow it down depending on the material and the conditions and the shape and the temperature of that object. And then what the last thing that we need in order to build a very basic circuit is going to be something that pushes those electrons, something that drives that electron flow that causes the current to happen in the first place. And that's going to be the voltage or the potential. So the voltage is the measure of the potential energy to the charge flowing through a circuit. So this is electrical potential energy. You might see this throughout different classes, throughout different times in your life. Anytime you're looking at electricity, you might hear it in a couple of different terms. Voltage, potential, electric potential, and electric potential energy are all the same thing. So we're going to call it voltage for the rest of this class because it fits into an equation that we're doing. But I want you to focus on the words electrical potential energy right now. And I want you to remember back, again, we can make a comparison to gravity. So in week 1, we talked about gravitational potential energy. This was when an object was lifted up off the surface of the Earth. When it was lifted up off the surface of the Earth, then it had gravitational potential energy. And the reason that it had gravitational potential energy is because it was being held away from something that it's attracted to. Masses are attracted to each other. So if we have some restraint that holds them away from each other, then that gives them the potential energy to do work. If you remove that restraint, then that object is going to come rushing down towards the surface of the Earth. And then, of course, there's a conversion of that potential energy to kinetic energy at the bottom. With electrical potential energy, we're going to have kind of the exact same thing. We have, except for this time, the things that are attracted to each other are going to be opposite charges. So if you have a positive charge and a negative charge, and they're being restrained, they're being held away from each other through some sort of restraint. Obviously, it's not going to be a string and some scissors around a subatomic particle, but regardless, if you're holding two charges away from each other, then there's potential energy, because if you remove that restraint, then those two objects are going to go rushing towards each other. So pulling something away from something else that it's attracted to gives that object a potential energy. So a good example of this, and probably one of the first things that popped into your head when I said voltage, is batteries. Batteries have two terminals. They have a positive terminal and a negative terminal. They're electrically isolated from each other when you just have a battery sitting by itself. So that battery has potential energy. It has voltage. And when you connect those two terminals with a wire or anything metal between them, maybe some tinfoil or something like that, then that removes the restraint that's holding them apart, connects them, and allows those charged particles to flow from one terminal to the other. And all three of these things are combined in one of the most important laws in physics, or at least in electricity, a very important law. And you're going to be using this to do your simulation for this week. So Ohm's law relates these three values. We have the current, which is measured in amps, the resistance measured in ohms, and the voltage, which is measured in volts. And Ohm's law says that voltage is equal to current times resistance. So pretty simple, uh, straightforward equation, nothing crazy in it. If you guys, I'm not even going to go into this because if you don't want to use this triangle, if it's something you've seen before, then you can use it. But I think I went over it with F equal ma as well. Okay, so John said you've seen it before. If you like it, you can use it. If not, then just ignore this little part right here. Basically, the triangle it's an algebraic tool to figure out the different forms of the equation depending on what you want to solve for. So the trick for it is to cover the variable. You need to put the variables in the triangle in that way, and then you cover the variable that you are solving for, and then do the resulting calculation, which is either multiplication if those two variables are right next to each other, or division if there's one on top of the other. So right away we have one form of the equation on screen there. If we wanted to solve for the voltage, we would cover up the V, and then since I and R are right next to each other, we know that that indicates multiplication, so we would do current times resistance. If you wanted to solve for resistance, you would cover up the R. What's left is V over I, so over another thing indicates division, so voltage divided by current. And then if you wanted to solve for current, you cover up the I, and then you do voltage divided by resistance. I'll show you a couple of examples here using the three different forms of the equation. So a 9-volt battery is connected to a circuit. If the total resistance in the circuit is 4.5 ohms, what is the total current flowing through the circuit? So I'm given the voltage. I know 9 volts, and I know that ohms is a unit for resistance, so that's my that's 4.5. If I want to know the current, then I would go to my triangle, or I would just algebraically solve, and I end up with current equals voltage divided by resistance. And then I simply plug in my values. 9 divided by 4.5 is equal to 2 amps. All right, the second one, a battery is connected to a circuit. If the current flowing through the circuit is 2.5 amps and the total resistance in the circuit is 6 ohms, what is the electric potential voltage of the battery? So this time I'm given current and resistance, and I want to solve for the voltage. So the form of the equation that I want to use is voltage equals current times resistance. So I simply plug in and multiply my two values together. 2.5 amps is the current times the resistance, which is 6 ohms, and that is equal to a total of 15 volts. And then I'll beat the dead horse with all the three different ways we could do this here. And we have a 12-volt battery. It's connected to a circuit. If the total current flowing through the circuit is 4 amps, then what is the total resistance of that circuit? Here I'm given voltage and current. If I want to solve for the resistance, I would use my final form of the equation, R equals V over I. Voltage is 12, current is 4. 12 divided by 4 is equal to 3, and my units for resistance are ohms. All right, any questions on any of those three different characteristics of a circuit or solving for Ohm's law? All right. So we have mentioned circuit. I have mentioned circuit a couple of times. Now I think it's probably a good time, maybe should have done it a while ago, to define a circuit. An electric circuit is any closed path along which electrons can flow. So in order for continuous flow to occur for a circuit to be functional, then there cannot be gaps in between that circuit. An open electric switch does this. It provides a gap, it breaks the circuit, and it's like switching a light on and off. When you turn that light on, that closes the circuit. When you flip it off, it breaks the circuit so that the electrons can no longer flow. So we need a closed path for that to take. We have two different types of circuits, and this is exactly what your simulation is on for this week. We're going to ask you to build these two different types of circuits, and then also, I believe, a combination between the two, but maybe not. Maybe I'm thinking the wrong thing. But anyway, two different types of circuit. We have a series circuit, and a series circuit is any circuit that provides only one single pathway for electrons to flow. So this means that if there's a break anywhere in the path that makes that circuit become open, then the entire thing stops working. So you can see in the picture here, this would be a very simple example of a series circuit. We have a battery, and we have a wire connected to the positive and negative terminals of that battery. And then across that wire, we have 4 light bulbs that are are connected in series inside of the circuit. So if you think about the path of a single electron, it only has, coming out of that battery and flowing through the wire, it only has one path it can take to get to the other terminal. Yeah, it is. And that's John asks, why would you do that? It makes it hard to find the one that is not working. Absolutely. This is this is it's a very simplified circuit. It's a lot less common than the other type of circuit, which is a parallel circuit. There are a couple of minor advantages to series, mostly simplicity, but only if you don't have to troubleshoot anything. So basically what this does is so if you think about one single electron, the electron goes through one light bulb, it goes through the other one, the other one, the other one. So it has to go the whole way through. It has to go through every component. So what this means is that if one of those light bulbs goes out, then the whole circuit is broken. And the example that I always used was old Christmas lights, and it might be what you guys are thinking of as well, because if you had a string of Christmas lights and then one of the bulbs went out and the whole thing went out, then you had to go through and test every single bulb and try to replace it. So that's definitely the way that it used to be. I used to say that to my Canvas classes, and then they told me that apparently there's been great advancements in Christmas light technology, because I guess they're connected in parallel now, so that a light bulb can go out and it doesn't break the whole circuit. But they definitely used to be like that, because I remember trying to find them all the time, and it was very annoying. All right, so what we're going to ask you to calculate in that in your simulation, we might ask you to calculate the resistance in a series circuit. Martha, you're right. There is something about trying to find that one light, and you feel really, really good when you find it. All right, so if we asked you to calculate the resistance in a series circuit, it's a very simple equation, even though it might not look like it is in that in what I have on screen there, which is just the generalized version of the resistance in a series circuit. All you do in a series circuit is, to find the total resistance of that circuit, is add together all of the individual resistors. So if you have 4 light bulbs, you need to know the resistance of all 4 of them, and then you simply add them together. So an example of that here, we have a series circuit here that has 2 10-ohm resistors connected in series, connected to a 12-volt source. And if we wanted to calculate the total resistance of this circuit, it would just simply be 10 ohms plus 10 ohms is equal to 20 ohms. So in a series circuit, very simple, just add them together. If we added one more resistor, and this could be a light bulb could be a resistor. If we added one more resistor in parallel, then that would mean we would just do, instead of 10 plus 10, we would do 10 plus 10 plus 10, and end up with a total resistance of 30 ohms. So that equation that I showed you, there it is. On that last screen, what that R1 plus R2 plus R3 plus dot 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 plus R to the N just means that however many resistors there are inside of that circuit, then you just add those together. So 20 ohms, 30 ohms. This is where I was supposed to write stuff, but my thing's not working. So hopefully you guys can visualize that equation, and it's pretty simple with a series circuit. But one thing that I did not do, which you could do, and I think we ask you to do, is to solve for the total current in a circuit just given this information. So if you were given this exact problem, then you know that the voltage is 12. You've added together the resistors, so you know that the total resistance of the circuit is 20. And if you were asked to solve for the current, you could use Ohm's law, because you have voltage and resistance, to solve for that current. So that calculation would be current is equal to voltage divided by resistance, 12 divided by 20. And so if I do some math in my head, it'd be 6 over 5, 1.2, no, 12 divided by 20, 6 over 10, 3/5. So it'd be 0.6 amps. Sheesh. Just got back from vacation. Mental math is hard. All right, so then if we add in one more resistor here, then you have 10 ohms plus 10 ohms plus 10 ohms. Your total resistance of that circuit is going to be 30. And then you can use the exact same equation, current equals voltage divided by resistance. And what you end up with now is 12 divided by 30. So that, I'm not getting the math here, but 6 over 15 reduced 2 over 5. Okay, so 0.4. Thank you, John. I really appreciate that. I'm going to mess this up one of these times. So, all right, so 0.6 amps before, and now we're down to 0.4. So the conclusion that we were coming up to is that in a series circuit, adding more resistors is going to increase the total resistance, so the current flowing through the circuit decreases. When we added one more resistor in that second example, our current decreased from 0.6 amps to 0.4 amps. You got it. So in a series circuit, that's why they're called resistors. The more you add, the more they resist. But it's going to be a little bit different if you connect it in a different way, which is kind of counterintuitive here for our next example. So the next type of circuit that we have is called a parallel circuit. A parallel circuit is going to offer more than one path for those electrons to take. So this means that if there's a break in the path, if one of your light bulbs goes out, then that doesn't mean that your whole circuit is broken, because those electrons can go down different branches. They don't have to travel through every single component in order to complete the circuit. So the equation for calculating the resistance in parallel is going to be slightly more complicated, just because now we're adding fractions into it. And what it turns out to be is that it's not adding together the resistors straight. It's adding together the inverses of all the individual resistors. So we had 1 over the total resistance equals 1 over R1 plus 1 over R2 plus 1 over R3 for however many resistors are inside of that circuit. So our example here, and hopefully I have this right now because I do on the next one. All right, so the first one, we have the exact same components of our series example. We have 12 volts for our voltage source. We have two 10 ohm resistors, but this time, instead of being connected in series, they're going to be connected in parallel. So in order to figure out the total resistance of this circuit, I need to add together the inverses of those individual resistors. So instead of just 10 plus 10, we have 1 over 10 plus 1 over 10 is going to be equal to 2 over 10. And, oh man, I really wish I could write. It's killing me. Go back. All right, so if you look at the equation, you can see we have 1 over our total equals, and what we just solved for when we added together the inverses of those resistors is 2 over 10. So we ended up with 1 over r equals 2 over 10. Now, a lot of people, and one of the most common errors when solving for resistors and resistance in parallel is to stop right there. Say, okay, I got 2 over 10 equals something on the other side. Sounds like I'm done. But you're not, because you haven't solved for the total resistance. You've solved for 1 over the total resistance. So what you need to do is, what I like to do, there's a couple different ways to do it, is cross multiply. So you have 1 over r equals 2 over 10. And so if you cross multiply, you get 2 times r equals 1 times 10. And that means 2r equals 10. And then divide both sides by 2. And what you end up with is a total of 5 ohms. All right. So I have this written out on the next one, thank goodness, so I can give you guys a little visual here. Let me just mention that, again, you could do the exact same process using Ohm's law to calculate the current by dividing the 12 volts by the 5 ohms that we just figured out. So 12 divided by 5, someone want to do that? It's just 2.4. Anyone want to check me on that? Awesome, good. I should really have a calculator nearby. All right, so it's 2.4. So 2.4 amps is what the total amount of current would be here. And you can already see that just taking the same components of the circuit and just rearranging them in a different way, our current has already increased a lot. Before, when we had the resistors connected in series, then that current, the total current flowing through, is only about 0.4. Now we've just taken them and connected them in a different way, and now the current's 2.4. So keeping that in mind, let's see what happens when we add one more resistor to this circuit. So now we have 3. It's not so much, that's a great question, Martha. Is this because the distance has changed as well? It's not so much the distance. It's more the fact that it doesn't have to go through every single component. So that last, if you imagine one electron going through the series, then it goes through one, which resists it, and then it goes through another one, which also resists it. So that increases the resistance, and now it only has to go through one if it wants to. Yeah, no problem. That's a great question. The distance does depend. The distance that electricity has to travel does affect the resistance. If it's a longer wire, then that increases the resistance as well. So you're absolutely correct on that. That distance does affect it. But we're just looking at the components inside of it right now. All right. So 1 over the total resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So here, because we added one more resistor, that just adds one more term to our equation. And now we just plug in our values. Luckily, these are all the same denominators, 1 over 10 plus 1 over 10 plus 1 over 10. If they weren't, please remember that you need to find a common denominator before you add those fractions together. But what we end up with here is 1 over the total resistance equals 3 over 10. Again, we don't want to stop here because we haven't solved for the total resistance. We've solved for the inverse of the total resistance. So what we need to do, or what I like to do, is to set this up as a cross multiplication problem, because we have it exactly in that format where two fractions are equal to each other. And we would do 1 times 10 is equal to the total resistance, which times 3, and then 1 times 10 is just 10, and then that equals to 3 times the total resistance. So now 10 divide both sides by 3, and we end up with a total resistance of 3.33 ohms. So here we can see what happened to the total resistance when this is opposite of what happened in series. When we added one more resistor to this circuit, then it actually decreased the amount of total resistance of that circuit. So if we solved for the current in this case, then that means that there would be an increase in the current because the total resistance actually goes down. The more adding more resistors in parallel actually decreases the total resistance and increases the amount of current that's flowing through the circuit. And this is something that we definitely need to pay attention to for safety reasons. If you connect a ton of things in the same parallel circuit, then that's going to increase your total current. And as more and more devices are going to be connected, then more current flows through that wire. Every device can only handle a certain amount of current before it overheats, and excessive current can result in a fire. But we, of course, have safety measures to prevent that. Most likely you have circuit breakers in your home, so if the current gets too high, then it just shuts down the whole circuit before it gets too dangerous. Also, not quite as common anymore, but used a lot before, were safety fuses that were attached to the wires, and they would actually melt if the current got too high. And when they melted, then that caused a break in the circuit and wouldn't allow those electrons to flow anymore. So we do have means to protect against it, but just keep in mind for safety reasons that parallel circuits, when you add more components into them, it decreases the total resistance and increases the amount of current. All right, and the last equation for electricity, before I'm just going to talk a little bit about magnetism, is the electric power. Power is measured in watts. You've probably, most likely, again, go back to the light bulb with this. The more power it has, the more wattage, the brighter that light's going to be. And the strict definition of it is the rate at which electricity is converted into another form. So when you connect a light bulb into a circuit, that electric energy is converted into light energy or photonic energy, and the rate at which that occurs is the power, is the wattage that you have that's written on that light bulb. And the equation form for that is the power is equal to the current times the voltage. So power is going to be directly proportional to both current and voltage, and so the more current is flowing, the more voltage is connected in that circuit, then the brighter your light bulb would shine. All right, so I want to talk a little bit about magnetism. It's not the biggest focus for us this week, but I do want to mention it because it is very closely related to electricity. And also the relationship between the two of them is something that's used in a lot of different devices in a process called electromagnetic induction, or maybe you've heard of an electromagnet before. So before I go into what makes something magnetic, do you guys have any questions on the last couple parts of the electricity lecture there? Okay, good. All right, easy enough. So magnetism is going to be another force that can be either attractive or repulsive. This time we're not dealing directly with positive and negative charges. We're going to refer to the things that are repelled or pulled together as poles. Maybe you've heard north and south pole on a magnet. But this force results from the atomic structure of a material. And it's due to the arrangement of the atoms inside of that material, and most importantly, its electrons. So if you think about, well, all right, so all magnetism is created by electric current. So that's something really important to remember, and it also deals with the relationship between the two. Magnetism occurs because of moving particles, moving charged particles. When a charged particle is sitting still, it is surrounded by an electric field. It has electric charges. As soon as it starts moving, it has both electric charges and magnetic. It has an electric field and a magnetic field. So if you think about the structure of an atom, again, going back to our discussions from last week, then we know that you have a positive charge in the middle, and then electrons are orbiting around that positive charge. So electrons on their own orbiting around a positively charged center orbiting around the nucleus are going to have their own individual magnetic fields because they are, by definition, charged particles in motion. So there's two different motions of an electron that causes that magnetism. We have and you can think about it, a very simplified way to think about it is like the planets orbiting the sun. So when a planet orbits the sun, it has an orbit, a revolution around the center, around the sun, and then it also has a rotation speed. It's spinning, and of course, again, this is a very simplified thing. We'll get into more detail next week, but the spin of the electrons and the orbit around that nucleus are going to both be motions that cause that magnetic field. So the magnetic field, every single atom has its own magnetic field. And if you can make all of those magnetic fields align with each other, then you end up with a magnet. And the reason that they need to be aligned is because magnetic field of an electron is a vector. So it has both a magnitude, it has an amount, and it also has a direction. If two electrons are spinning the same way and their magnetic fields are pointing the same way, then they're going to be added together and they're going to increase the total magnetic strength of that material. If they're pointing in opposite directions, then they're going to cancel each other out because they're considered anti-parallel fields and they're subtracted from one another. So the net magnetic field of an object is the addition and subtraction of all the individual atoms' magnetic fields pointing in different directions. So an unmagnetized material is something that doesn't act as a magnet, is going to have its electrons not aligned in any particular way, so that all the magnetic fields are pretty much going to cancel each other out. So a magnet is a material whose electrons that have more parallel fields, more electrons' magnetic fields acting in the same direction than anti-parallel fields. And the more you can get aligned in that parallel field, the more magnetic fields you're adding together, that's going to increase the strength of your magnet. All right, so when those magnetic fields are aligned, you end up with a north pole and a south pole. And just like the charges, opposite or like poles are going to repel each other, and opposite poles are going to attract each other. And then the last thing here is that you cannot have one pole without another. They are all dipoles, meaning that there are two poles, and you can't just have a single north pole without a south pole. So every magnet's going to have both. If you take a magnet and you cut it in half, say you look at the picture there, and you look at the image A, and you have the North Pole. If you take it right in the center where that red line interacts with that comes in contact with the gray line and you cut that magnet in half, that doesn't mean you're going to have a north pole on top, a south pole on the bottom. It will automatically gain another south pole, and the south pole will automatically gain another north pole. So every magnet has a north and south pole. The magnetic field lines are going to extend out of the north pole and point towards the south pole. So examples of different types of magnets are maybe something like a simple bar magnet, like you have in the picture on the right there. And in that case, the poles are at the opposite ends. With a horseshoe magnet, the poles are going to be at the ends as well, but it's just bent into a U shape. And then Earth is actually a really good example of a magnet. Earth has a magnetic field that surrounds it due to the magnetic nature at the center, the magnetic properties that occur at the center of the Earth. So I want to talk about that for just a second. Well, the first thing is that the magnetic North Pole and the magnetic South Pole are actually opposite of our geographic North and South Poles. So that means that the magnetic South Pole actually comes out somewhere around Canada, and the magnetic North Pole goes out somewhere around Antarctica. Just happens to be the way it worked out. It flips every once in a while. So the reason that the Earth has a magnetic field, that it acts like a magnet. There's a common misconception with that. A lot of people might say that they think that the Earth has a magnetic field surrounding it just because the core of the Earth, the inner core of the Earth, is iron. But the core of the Earth is actually almost as hot as the surface of the sun, and that is actually too hot to become magnetic, too much atomic motion to make those electrons line in any significant way. It's hotter than something called the Curie temperature, and past that temperature, you cannot create a magnet because the atomic motion is too erratic. So where Earth's magnetic field comes from is not from that inner core, it's actually from the outer core. The outer core of the Earth is also iron, but it's liquid iron. So it's made up of all these charged particles, and they're flowing in the same direction. They have a current to them due to the rotation of the Earth. So when the Earth rotates, the core rotates as well, and the motion of those charged particles and having them travel in the same direction aligns the atoms, aligns the spin, and it gives us a current, which gives us which allows the Earth to act like a magnet. So the magnetic field of the Earth extends out far beyond our atmosphere. You might have heard it referred to as the magnetosphere before, but the Earth's magnetic field lines extends far beyond even the top of our atmosphere, and it does a lot to protect us from charged particles and cosmic radiation. All right, so you've probably already gathered this because we've mentioned it a few times, but there is a really close connection between electricity and magnetism because they generate each other, they cause each other. So we've already stated that when an electric current flows through a wire, moving particles, every time we had moving charged particles, then a magnetic field forms around the wire. And if it's just a straight wire, then it forms in concentric circles and a concentric circle pattern around that wire. And then you can adjust the direction of that field by changing which direction the current is going. But if you take that wire and you bend it into a loop, then the electric field lines become more like what you see in the picture here. So instead of just being like looped around one single circle, they're going to pass through the center of this coil. And the more loops that you provide, the stronger that magnetic field is going to be. So the magnetic field intensity increases the more loops you put in your wire. And what this does is create something called an electromagnet. And electromagnetics and electromagnetic induction causing magnetic fields causing electricity causing magnetic fields is the basis for a lot of different objects that we use all the time, things like transformers and generators, just as a couple of examples there. So electromagnetism is the basis for a lot of things that we use inside of to generate electricity in a meaningful way. All right, guys. Well, that is the end of my electricity and magnetism lecture. I will stick around for a few more minutes. Well, again, I always say that. I'll stick around as long as you want if you have any questions on anything. But if not, then you guys are free to go. And I thank you for coming to lecture tonight. And I hope to see you. I have another session tonight, trying to get caught up from being on vacation. We'll talk about waves. We'll talk about sound and light. And we will do that tonight just in a couple hours at 5 p.m. if you guys want to come to that. But all right, well, thank you guys for coming, and I hope you enjoyed the lecture on electricity and magnetism.